Hello and welcome back to the course. Do you remember when we were talking about sine wave, triangle and sawtooth types of signals? And I mentioned in that lecture that those are not all the types of signals that you will find in electronics. And in today's course, we will be focusing more on the square wave type of signal, which is the second most popular signal after sine wave. But before getting into square waves, let's understand first what are pulses. A pulse is a signal that looks like in the figure on the right. It is defined by amplitude and pulse width. You can generate a train of periodic pulses, in which case you can talk about the frequency or pulse repetition rate and the duty cycle. It is very important to understand what is duty cycle when we are talking about square waves. So it's nothing else but the measure of system active time. So duty cycle basically is the measure of the percentage that what percent of the load is on compared to off load. And as you might see from the diagram, as the duty cycle increases from 0 to 100, the time that the signal stays on the on state is increasing. This is a very powerful concept in electronics, and in the future courses we will build circuits that is using square waves, and we will understand how changing the duty cycle of the square wave will affect our circuit. But if you are impatient and curious, I can tell you that by changing the duty cycle of a square wave, we can basically control the speed of a DC motor. Now obviously this is not the only application where you can use square waves. These are universally encountered in digital switching circuits and are naturally generated by binary logic devices. They can be used as timing references or clock signals, but you don't have to worry about all this for the moment, okay? We will learn and examine all of this in the future lessons. Now let's get back where we left off. If you look at the diagram, you will see that pulses can have positive or negative polarity. In addition, they can be positive going or negative going. For instance, the second pulse is a negative going pulse of positive polarity. And now let's talk about square wave a little bit. A square wave is in time as shown in this figure. The square wave is just a special case of a pulse wave which allows arbitrary durations at minimum and maximum. A true square wave has a 50% duty cycle. And what does it mean? That equal high and low periods, right? Now, like the sine wave, it is characterized by amplitude and frequency. A linear circuit driven by a square wave rarely responds with a square wave. And it is good to know that for a square wave, the peak amplitude and the RMS amplitude are the same. Now this might sound disappointing, but the edges of a square wave are not perfectly square. In typical electronic circuits, the rise time ranges from a few nanoseconds to a few microseconds, and this rise time is conventionally defined as the time required for a signal to go from 10% to 90% of its total transition. And the reason behind the square wave is not actually a perfect square wave is because if you look at the frequency domain graph for the square wave, you will see that it contains a wide range of harmonics. Now this might sound strange to you, but when we are going to learn about Fourier series, you will understand that a square wave is basically composed of sine and cosine waves. And if you strive really hard to achieve a perfect square wave, in this case you will need harmonics of very high frequencies. And this is a problem because these high frequency harmonics will generate electromagnetic radiations or pulses of pulses of current that interfere with other nearby circuits, causing noise or errors. And another reason that you cannot achieve a perfect square wave, which means that the rise time is equal to 0, is because the component itself that is generating this square wave is not an ideal component. It has its own internal limitations, and exactly because of these limitations you cannot achieve really high switching frequencies. Okay, and now let's move further with our course, and let's talk a little bit about steps and spikes. Steps and spikes are signals that are talked about a lot but are not so often used. If you could, let's say, draw them, they would look something like in this figure. A step function is basically a part of a square wave, and a spike is simply a jump of vanishingly short duration. Now let's talk about logic levels, which is a subject that is more interesting than the previous one. Now, as you know, pulses and square waves are used extensively in digital electronics. And these pulses or square waves have a predefined voltage levels represented by one of two possible states. These states are called simply high and low and correspond to the 1 and 0 states of Boolean logic. Now, looking at the waveform that this circuit generates, when the signal reaches 5 volts, this is called the high logic 1, and when the signal is at 0 volt, this is called the low logic or 0. Now, the only language that microprocessors or microcontrollers understand is binary language, right? Which is just a bunch of ones and zeros. And these ones corresponds to high logic and 0 corresponds to low logic. Alright, so let's have a look at this circuit and let's see how we can generate logic high and logic low. So we have a source, a 5 volt voltage source, we have a resistor, and we have a switch. This circuit is similar to the voltage divider, isn't it? So now we have two possibilities. If the switch is open, we get here 5 volts because the current will try to flow in this direction, right? And let me ask you a question. Why do you think this resistor is here? Well, this resistor is here because when we close the switch, this point here will be pulled to the ground, right? And because we don't want to create short circuit between the voltage source and the ground, we need to place this resistor here so that we limit the current that is flowing between the voltage source and the ground. Otherwise the current will be too high and we can damage our circuit. Alright, so this was it. Thanks for watching and see you in the next course.